Hi, welcome to this particular lab class. In this lab class we will show it to you how to fabricate the microfluidic chip, and this device will be used for as a biochip and with PDMS as a material, and also will show you how the molding will work or how we can use mold for creating channels in PDMS. So, what exactly mold means, right. So, if you see the screen, if I have silicon wafer, right, and if I grow silicon dioxide, let us say I am growing 1 micron of silicon dioxide. Now, you already know that if we use LPCVD, then we can grow silicon dioxide on both the surfaces of silicon wafer. This is silicon dioxide, this is silicon, this is silicon dioxide. Now, if I go for photolithography, which is you know how to do photolithography, right. Photolithography, spin coat, photoresist, then soft bake. Soft bake is done at 90 degree centigrade for 1 minute on hot plate. Next step is you load mask and expose the wafer which is spin coated with photoresist. Next step is you develop photoresist. After that you hard bake. Hard bake is done at 120 degree centigrade 1 minute on hot plate, followed by inspection. Inspection is done in using microscope, right. So, these are the steps for your photolithography. So, once I perform photolithography, what I will do here is that I will create a window into silicon dioxide and then I will etch the silicon through that window. What does that mean? If I perform photolithography, I will be creating a wafer. I will say this is an oxidized silicon wafer, and I will protect my photoresist in all the area except in the center. So, this is my photoresist, and as you can see there is a window, right. So, if I dip this wafer, this is my photoresist, let us say positive photoresist. If I dip this wafer in BHF, which is buffer hydrofluoric acid, what will happen? My silicon dioxide will get H. Silicon dioxide will get H. In reality, the silicon dioxide from the back side will also get H, because I do not have any protection on the back side. So, now what will happen? You have H silicon dioxide by dipping the wafer in BHF. After this, if I further dip this wafer in acetone, what will happen? The photoresist that is here will be etched or will be stripped off. Acetone is a stripper for photoresist. After this, if I dip this wafer in silicon etchant, you know what are silicon etchants? Silicon etchants are KOH, potassium hydroxide, TMAH, tetramethyl ammonium hydroxide, right, and you know the advantage and disadvantage of both the materials. Also, these are wet etching, but if I go for DRI, which is your dry etching, is a deep reactive ion etching. So, if I etch silicon like this, all right, by dipping the wafer in silicon etchant, what I have? I have a structure in an oxidized silicon wafer. Now, if I dip this wafer further into BHF, what will happen? If I dip this wafer further in BHF, then what will happen? This silicon dioxide will get etched, right, and I will have silicon like this. So, this silicon will act as a mold. People write in a different way, MOULD is correct, MOLD is also correct, all right. So, we will have a mold on which if I spin coat or if I pour PDMS, this is my PDMS, and cure it. After curing, I can strip it off. What will I have? I will have PDMS structure like this, right. So, after I strip it off, I can get back my mold, and I have already patterned my PDMS using this particular silicon mold. Again, if I pour, I can cure and I can create another structure. You can create as many structures as you want, and that is why this is a part of your soft lithography as well. So, in this class we will see the mold and how to create the silicon PDMS molding, how to fabricate microfluidic device with PDMS, and I will invite now my student Anil to again show it to you how to use this particular technique, right. If you have any questions, feel free to ask. I will see you in the next class where we will be actually showing it to you how to compare microfluidic chip with and without PDMS molding and what are their applications. Right. Till then you take care. I will see you in the next class. Bye.
Welcome. Today we start a series of short modules where we show you different types of microfabricated sensors that we have made in our lab and which we would like to show you as part of our course. The idea is, I think in previous modules you have seen ready-made commercial sensors and actuators and how they have been interfaced with microcontroller boards like Arduino, etc. Now today where we start a series of modules where we show you microfabricated sensors. So these are not commercial sensors, but we have fabricated in-house using the different techniques of microfabrication that you have learned as part of this course, like photolithography, deposition, like chemical vapor deposition, physical vapor deposition, lithography, etching, all those methods, and then few packaging concepts like bonding, wire bonding, anodic bonding, oxygen plasma bonding, etc. Okay. So, professor would have covered different types of substrates on which such sensors are made, right. One type of substrate is silicon substrate, then you have glass substrate, then you have silicon on insulator substrate. So, different types of substrates are there. On this substrate you make these sensors using different materials like gold, platinum, molybdenum, titanium. Lot of materials are there which you can use to make these devices. One very big class of sensors are the microfluidic devices which allow for fluid flow in the micro scale like microliters per minute, and also allows for sensors to be kept below the channels. So, it can become a dynamic system. You have a liquid, you can either have a static system or a dynamic system. Let us say you have a liquid, few drops of liquid, and you want to analyze what is there inside the liquid, the constituents of the liquid. You can either drop that liquid onto a static well which contains sensors below, or you can flow that liquid through a microfluidic channel with sensors below it. The flow through a microfluidic channel is a more dynamic system and it might emulate original real world conditions like blood flow in the body. So, that is why microfluidic systems are used. So, today I am showing you a microfluidic device. You can see it in my hand. So, I have the microfluidic device in my hand, correct. So, if you can, as you can see, if I tilt it like this thick membrane here forms the microfluidic channel. This is PDMS, okay, polydimethyl siloxane. PDMS is the usual material that is used to make microfluidic channels. But from a translational point of view, if you look at a product, usually PDMS is not used. Instead, you use acrylic sheets or PMMA sheets. That is here next to me. These are acrylic sheets. So, these are acrylic sheets. They are very thick, right? See, I am doing this. Nothing happens to them. So, they are very robust. So, it can be handled in a real world practical scenario. You can make channels. You can see the white color channels here. You can make channels by laser cutting these acrylic sheets. Okay, that is one way of industrially making microfluidic chips. But in a research domain, usually PDMS is used because they are really easy to work with and fabricate. Okay. Now, if you look at this microfluidic chip, you have the electrodes. You can see gold pads here, right? And there is a sensor at the bottom. So, you can see 3 sensors here. So, those are interdigitated electrodes and the contact pads are coming here. These are gold interdigitated electrodes with the contact pads coming here. Okay. Now, what we have done is we have made microfluidic channels underneath this PDMS membrane, and the channels are coming and sitting on top of these interdigitated electrodes. Then we will measure outside the microfluidic channel here using these contact pads. These pipes that you are seeing here, you can see these pipes, right? So these pipes are the ports for inlet outlet where you flow the liquid. These are very fine 0.14 millimeter dia microfluidic tubes. They are called MFTs or microfluidic tubes, and they can be connected to a peristaltic pump or a syringe pump using microfluidic connectors or MFCs. Okay. So you have a pair of inlet ports. So you connect one end of the peristaltic pump here, other end here, and you can flow a liquid through this, and you can load samples through other channels. As a result, you can keep flowing it, like you can flow blood, and if the blood contains, let's say, some chemical, you can capture that chemical in these electrodes, in these chambers. These are chambers here. You can capture these analytes in these chambers and then see their electrical response. So this is a very simple way of making a microfluidic sensor. Okay, here we are actuating the flow of the liquid and sensing contents from the liquid. So this is a sensor and actuator. So this is a very useful biomedical application. There is a very useful biomedical application for this chip because it is point of care. You just need very small sample volumes. You can just put it and it will immediately show you result if you connect it to a system that can measure impedance from this microfluidic chip. So this is how a microfluidic chip looks like. This is from a research point of view. If you want to make a product will look like this. So you can easily make it, you can handle it in a very robust manner. It can be given to a lab technician, they can handle it, they can be trained very fast, and you can connect this same connectors to this end and do the same work that is done by this. Only limitation, if you look at it, is this PDMS is fabricated by pouring molten PDMS. I think you would have seen in a previous lecture, by pouring molten PDMS onto a silicon substrate that has the pattern. Because the pattern is on a silicon substrate and you will use conventional microfabrication techniques, you can go to very fine dimensions for the channels, like up to, we can even go to 100 micron channels, 200 micron channels. But these are mass produced microfluidic chips. These also we have made in our lab. These are mass produced microfluidic chips, but because these are mass produced, they don't employ the complex microfabrication techniques. Instead we use very fine laser cutting. As a result, we might not get up to 100 micron or 50 micron feature size, but we can work with around 300-400 microns or 0.3-0.4 mm, which is good enough if you look at it. So it's a trade-off between extreme accuracy and applicability or translatable nature of technology. So what you do is you prove your technology with the most accuracy and sensitivity on a platform like this, because first of all you need to prove your technology. For that, your sensitivity and accuracy has to be extremely high, and many times even more than what is required. Once you know your technology is working, you set benchmarks for your accuracy and sensitivity. You can move on to a platform like this where you know that it is okay to have a slightly lesser accuracy, and which you can trade off for manufacturability. This is easy to manufacture, especially for mass manufacturing. So that is how you make design decisions, and that is how you make a technology, a research outcome translatable into a final product that can be sold in the market and can change the lives of people. So that is microfluidic technology for you. Like this, we will see other sensors that we have fabricated in the lab, what are the method, what are the underlying principle of sensing, and how they are applied in a real life scenario. Thank you, hope you found this useful. Hi, in the previous short module, you saw how a microfluidic device is designed and what is the application and what is the utility of using microfluidic technology. Today we will see a small extension of this in two different microfluidic techniques. So let's see the devices now. So this is the microfluidic device that you already saw in the previous module, correct? So the PDMS membrane was there, you had a glass slide. I forgot to tell one thing, is that how is the glass slide bonded to this PDMS membrane is through oxygen plasma bonding. What you do is, we have seen this in the oxygen plasma system in the lab. So you activate the surface with oxygen plasma, you activate both the surfaces and then you put them together, they will bond. That is another process, okay. So this sensor you have seen. So without the PDMS membrane, I am showing you another sensor, okay. So I am not sure whether you are able to see the features, so let me just put with the tissue paper. Okay, now I think you are able to see it. See, if you see, these contact pads are there, these are gold, and you can see 3 sensors like we saw last time. But if you look closely, there is another layer below it. Okay, that is made of nichrome. Okay, so that what it is it's a spiral structure. As you can see, it's continuously spiraling. This is actually a micro heater. So we have a micro heater and electrodes on top of it. So what is the utility of such a structure is that, let's say you are working with live samples. Let's say you are trying to measure the impedance of live cells, live mammalian cells or live bacterial cells, and you are continuously measuring it over a period of 1 day or 24 hours. Now you will be flowing the cells in their nutrient rich media so that they can survive. But then for cells to survive, they also need 37 degrees Celsius temperature. So how do you maintain that 37 degrees Celsius temperature? For that, we need to have such micro heaters. This micro heater, we will supply voltage to this micro heater and it will be heated up. And it can be controlled to be maintained at a particular temperature, let's say plus or minus 0.5 degree. So between 29 to 36.5 to 37.5 degree, this heater's temperature can be maintained, or even closer depending on how accurate your control system is. So the heater will be maintained, so the cells will be flowing like in the previous microfluidic channel, but the cells will also feel the 37 degrees Celsius, which is the internal body temperature. So we are recreating the in vivo scenario in this microfluidic platform. As a result, whatever sensed data comes out will be closer to an in vivo measurement. That is the overall design ideology or philosophy. So you are flowing it at the flow rate which is equivalent to the flow rate of blood. Then you are maintaining the inside body temperature which is 37 degrees Celsius. Your channels are also designed to be mimicking the channel length of the blood vessels. So your mechanical constrictions or mechanical constraints of your blood vessel is met. The mechanical flow constraints of your blood vessel is replicated in this microfluidic channels, as well as the thermal environment inside your body, which is 37 degrees Celsius, is also recreated. How wonderful is that? That is the advantage of microfluidic technology. So you can recreate all these things, as a result of which your measurements from your sensing or your experiments will be as close as possible to the in vivo scenario. The truth remains that you can never completely mimic your in vivo or what happens in your inside your body, but you can get as close as possible. That is the pursuit of science. So this way you are able to do that. That is the advantage of microfluidic technology, and that is the advantage of incorporating a micro sensor into these electrodes which you saw. So this is I am adding one sophistication onto another of the previous design that we saw, so that you understand the design process and how a requirement from real world comes down to a design in the sensor world. So that is the overall idea. I hope this idea came across to you in a very good manner, and we will keep seeing these short modules. Thank you.